Okay, today's lecture will be about parameter identification in the context of ordinary differential equations. So it's when you have a parameter in a differential equation model for a physical process and you wish to identify or determine the value of a parameter in that ODE from data. Time series data, because we're dealing with differential equations that are initial condition or initial value problems. Could be boundary value problems too. So what we're going to deal with today, it's real data from an Arduino, and it concerns a thermistor. Thermistors are often used as temperature sensors, and I use this as an example in my process dynamics class because it illustrates the fact that sensors take a while to respond. In this case, this temperature sensor is going to take a while to equilibrate with the air temperature, the air that's in contact with it, and that's because the thermistor itself has a thermal mass. So imagine that the air jumps up in temperature. It's going to take a while for that air to heat up the thermistor and for the thermistor to equilibrate in temperature of the air. And that has implications because now your sensor has a response time. You have to wait for that thermal equilibration to occur before you can get an idea of what the true temperature is of the air. But in this class, we're just going to use it as a nice example of parameter identification for an ODE. And then for your activity, you'll do parameter identification in the SIR model, which is more complicated than this because SIR model has multiple ODEs. This is just one. So here's your experimental setup. Grant is a student who ran this experiment, and what he did is he grabbed onto this thermistor and held onto it for a long time, and the thermistor equilibrated with his body temperature. So it's hot. Hotter than the air, at least. And now what Grant did is he let go of this thermistor, and the thermistor's hot, so what happens is the thermistor loses heat to the air, and then slowly the thermistor equilibrates with the temperature of the air. And there's a time constant associated with that, with those dynamics, and we want to identify that time constant. Okay? So we're going to let TH, H for human, be the temperature of Grant, or just the human body temperature. And TA be the ambient temperature, that's the temperature of the air. So the thermistor is really going to go from TH, and it's going to drop in temperature slowly and approach TA, the temperature of the air. And a time constant is a characteristic time scale for how long it takes for that to happen, but it's more mathematically defined. This differential equation, which I derive for you in the inverse problems lecture. So watch that first before this. So this differential equation governs the dynamics of the temperature of the thermistor. So the rate of change of the temperature of the thermistor is proportional to the difference in temperature between the air and the thermistor itself. The time constant tau, the parameter we wish to identify, is here, and it's subject to an initial condition. So at time 0, that's going to be the time at which Grant let go of this thermistor. The temperature was equal to Grant's body temperature, TH. Yeah, so the goal is to identify tau. How exactly will we do that mathematically? Well, we have time series data, which I'll show you down here. I'll just show you. So here I've loaded in the time series data. This is real data from an Arduino. All right, so here's the time, and here's the temperature that was read by the thermistor. All right, and here's a plot of this temperature. Here's time, and here's the temperature of the thermistor. And then 35 degrees C, this is the temperature of the thermistor when Grant was holding it. All right, and this is the temperature of the air, a little bit below 20 degrees C. So you can see it was really hot, and then Grant let go at T equals 0, and the thermistor dropped in temperature and approached the air temperature. It's a very nice curve. For being real data, this is an awesome shape here. You'll see that the model fits the data really well. Okay, so I just loaded in the data and plotted it here. Now what we want to do is find the tau in this differential equation that gives a T of t curve that matches this data. So we want to find the tau that makes the model predictions go through this curve, through this data. So we're going to define a loss function, all right? And it describes the difference between this time series data here. This is a mathematical way of writing the data as time temperature pairs. There's n of them, capital N of them. We're going to loop through all of these data and sum up the squared differences between the temperature according to the data, so the real temperature that we measured, and the temperature predicted by the model at that same time for that particular tau. So you're thinking of this loss L as a function of tau, and if you change tau, you have a knob and you tune tau, the loss is going to change. You want to tune tau to minimize the loss, because that's going to give you the tau such that the model most closely matches the data. So the loss penalizes deviations in the model from the data points. All right. The optimal tau is argmin of your loss function. Okay, so that's what we're going to do. All right, first what we need to do is calculate the temperature of Grant's hand. And what we're going to do is do that by just looking at the data when t is less than 0 and taking the average of it. So we'll do a filter here. So let's filter our data. All right. And the first option to filter is a function that takes in rows. And we're going to look at the time. And we're going to see if that time is less than 0. And if it is, we want to keep that. Okay. Okay. And so here you can see all of the times in this data is now less than 0. Okay. And now we want to look at the temperature. Okay. So this is going to give you this column. And we want to look at the mean of that. Okay. So it's just the mean temperature right here. And it's a bit above 35, which is what it looks like. So let's define that as TH, because we're going to use that later. Define that as a variable TH. Okay. And then same for TA. We're going to look at when the temperature is greater than 40 and define that to be TA, the temperature of the air. Because, you know, eventually the thermistor is going to equilibrate with the air. And so we're basically assuming that pretty much the thermistor is equilibrated with the air temperature there. So TA equals mean, and we're going to do the same thing. Just do the same thing. But now, instead of looking at when the time is less than 0, we're going to see if it's greater than 40. We should get a little bit below 20, so we get 21. Okay, so we can even do a bit later, maybe, you know, like 40, 41. Oh, this would be, yeah, 40. 19, yeah, that makes sense, below 20. I was like, what? Yeah, so this is below 20. So we're looking at when all the times are greater than 40, so we're really only looking at this data here and taking the average of it. And you could go a bit more, you know, maybe 41 is better. 41 or 42 even, yeah. I'll give you that. All right, and so to check that these make sense, instead of eyeballing it, let's actually plot them here. So make this figure 2. Okay, we still want to plot the data. But now, in addition to that, what we want to do is plot these. So we're going to plot, we're going to make an H line. So H line stands for horizontal line. You got to put this axis here, and then we'll put TH. All right, we'll give that a label. So TH, and this is going to be degree C. Okay, and then we want to put a legend there to indicate which is which. So this is going to be T underscore A, which is the temperature of the air. Just to make sure we get these right, we'll give it an axis legend. Okay. Let's see what it looks like here. Yeah, so here we've got TA. Oh, it looks great. Goes right through the data, so that makes sense. It's always good to check your variables visually and make a visualization. So if you want to make these dashed, you can say, make that dashed. Okay, oh yeah, and there we go. So we've got the air temperature and the human temperature. So it goes from the temperature of the hand, and when you let it go, it equilibrates to the air temperature. Great. Okay, now that we've got those parameters, we're going to use differential equations.jl to set up an ODE solver. Okay, so this really has an analytical solution, but I just want to get you introduced to differential equations.jl. It's a really great package for solving differential equations numerically in Julia. Uses finite difference methods. And so what I do when I want to solve an ODE is just go to this page and try to mimic the examples. So ours is a scalar differential equation. There's just one variable. In your activity, you're going to scroll down and look at the system of differential equations, okay? So it's a bit of an extension of what we're doing here. Okay? So yes, we'll just mimic differential equations, all right? All right, so first, what you do is you view the differential equation as follows. So it has a right-hand side, f of u pt, except u here is rt. So we'll write f of t, and then the parameter that we have is tau, okay? So here P stands for parameters, T is time. Ours isn't explicitly a function of time. It's not in your activity either, so you can kind of ignore this, but you have to put it in for Julia. But yeah, so the right-hand side of the ODE is a function of the state itself and some parameters. Okay, and our parameter is tau. Okay, so this is the right-hand side, and you just define this. So this is equal to, and we'll scroll up to our ODE. So here's the ODE. So dt. If you divide by tau, it's ta minus t over tau. A minus t. It's going to pull ta from outside the function, and that's okay. You could make ta a parameter, but it's not. We're not going to ever change it, so I prefer not to. And it's that easy. This is how you define your differential equation, and it's understood that dt equals this. Okay, this is understood. Okay, all right, and then we got to define a time span over which we want to solve the ODE. You can say, okay, you want to go from 0 to around 50. So make that a tuple. Make that a tuple. 0.0 to 50. These are seconds. I like to put the units there. Okay. And then what I would like to do is write a function to do this, solve ODE, because I want to solve the ODE for many different taus. Remember, we're going to think of a knob where you tune it and it changes tau. I'm going to keep solving the ODE for different tau until the model curve goes through this data. So that's why I'm writing as a function of tau. We're not going to solve it once, we're going to solve it many times. Okay. So the way it works is you define a problem. So this is the ODE problem. You pass in your right-hand side of the ODE, and that kind of tells it what it is. And you also need to give it an initial condition, and that's the next argument. So the initial condition here is that it's at TH, right? So at time 0, the thermistor is at temperature TH right here. That's our initial condition, right? And then you give it the time span over which you'd like to numerically solve it. And then finally, you give it the tau that you want to pass in as the parameter here, okay? So remember, this is a function, so you could think of this as a p, and put a p here, put whatever there. I just put tau for clarity. But this is going to take this tau and pass it into this ODE problem, which is then going to understand, oh yeah, the parameter is the second argument of this function f, and use that tau to solve the ODE. Okay. So that defines the problem, and if you want to solve it, you say solve problem. And under the hood, differential equations does its business and solves the ODE. And then you return the solution, okay? And we can even call this t if you want, because it's going to really operate like a function, okay? And I'll show you that in a second. Let's say you want to solve the ODE for a particular tau, like time 15, okay? So if I solve a particular time, so this here means it's under the hood solving. What's nice is it's going to operate much like it's going to give you a data frame, but it's going to operate like a function. So now if I want to know what is the temperature at time 20, I can put in 20, see, it's like a function. It's like t of t. So this is temperature at t equals 20. Okay, so it's like a function, right? Which is really nice. So this is a numerical solution to your ODE. So it's that easy to solve an ODE in differential equations. All right, so we would like to plot this solution for this guess of tau. I just guessed that tau is 15, right? On top of the data to kind of see what it looks like. So let's do that. I'm going to copy this here. It changes to figure 3 so there's no conflicts. Okay, let's get rid of that. Okay. All right, and so now I would like to plot the model on top of that. Okay. So there's no there. Okay. So we're going to give this a label because later we're going to give it a label. So this is going to give it a legend. So this is going to be, this is your data. So I'll put TI. All right. So now there's going to be a label there. All right. And what I'd like to do is make an array of times. All right. So let's make T be a range from 0 up to about 45. And let's do 150 points there. This will make a nice range. And then I want to do is find t at each of these t's so I can plot them as an array. So if I do t dot t, it's going to apply this function element-wise over this array and give you a list of temperatures at those corresponding times. Okay. So now I'm just going to plot those. Lines t and t of t. All right, let's give that a label. So this is going to be t of t, and this is for tau equals 20. Okay. So we're going to plot the model. Oh yeah, and you can see here, oh, so first of all I need to go to a bit longer time, so let me go up to 50. Yeah. Okay, so this is your model and this is your data. And you can see that basically the heat transfer is a bit too slow. So it's taking too long to reach equilibrium, so tau needs to be a bit smaller. And so you can imagine you tune tau. So all right, let's make it a little bit smaller. Let's make it 18. Whoops, that's not gonna change it. Let's make it a bit smaller, and it's actually tau equals 15, sorry. Tau equals 15 from right here. Let's make it smaller. 12, ooh, we're getting there. See that? And so what I'm doing here is I'm changing it. Let's make it 5. Oh, now it's too small, right? But what you want to do is give this to an optimizer so it can do this for you and find the optimum tau, okay? So you're gonna keep tuning that. This is like our knob, right? So we know it's around 8. Yeah, see, now it's about through, okay? But you don't want to do this manually. You want to allow an optimizer to do it. And also when it's high dimensional, it's really difficult to do this, with your mouse. It's inefficient as well because the optimizer will take the fewest steps it needs to solve it, potentially, compared to what you do as a human. All right, so to do that, we're going to define a loss function. And it's going to be a function of tau because with different taus, we're going to have different losses. All right? And first thing we're going to do is solve the ODE with that tau, right? And then add up the loss. So we're going to say for row in each row of your data. And really, you only want to compare the data when time is greater than 0. So I'll say if row of time is greater than 0, then we add to the loss, okay? Plus equals, and then you look at the row of the temperature. So you're going to get the temperature. Where is it? It's over here. You're going to get the temperature of that row and compare it to what the model tells you. Minus t at that time. Okay? And you're going to square that up. Okay? So what you could really do here is if you wanted to make it really clear, I'll do that. So ti is going to be this, right? And ti, this is your data like in the formula. Okay, and if ti is greater than 0, that's the only time that we really want to do anything. Ignore the data for less than 0. So you're looking at the sum of square differences between the data temperature, the measured temperature, and the model prediction for that temperature. Okay, and finally, return L. Okay, and in this case, we can actually visualize the loss, which is kind of cool because it's one-dimensional. So let's say it's between 0 and 25. We know tau is somewhere in there. Length equals 45. All right. So we can actually visualize the loss. So I'll show you this. We're going to look at the loss. Figure 4. Okay. On the x-axis, we're going to have tau. So the tau that we choose, and then here we're going to have loss. Okay, and I'm going to show you what it looks like, okay? So for each of these taus, we're going to compute the loss. Okay? And what you're going to see is that there is a tau that minimizes the loss, okay? And this shows it nicely. So this is the tau that minimizes the loss, tau around 8, like we said. Tau's too big, the loss is big. If tau is too small, the loss is also big. So there's a sweet spot here. And what we want to do is find this. And you can kind of eyeball it to get it. But let's use an optimization routine to get it. Okay? So Julia has a really great optimization package, optim.jl, which I've loaded in. And for a scalar optimization problem, this is just a 1D optimization problem. You just have tau. It's quite easy. You just say optimize, what function you want to optimize, and give it a bracket. And here you know that the optimal tau is between 0 and 20, so let's tell it that. So look for an optimal tau between 0 and 20. All right? So it's using Brent's method. You can look that up. This is a search interval where it's searching for it. This is the minimum value of the function, and this is the minimizer. So the minimizer is the tau opt, which is 8.7, which is what we thought. So what I'll say is tau opt equals opt.optRes. If you hit tab, you can see the options, and I think minimizer is what we want. Minimizer, yep. So that's the optimal tau, right? So now that we've found the optimal tau right here, what we can do is resolve the ODE with that optimal tau and plot it, okay? So I'll say tau opt. This is the optimum function for t. I'm going to solve the ODE with my optimum value of tau, okay? And then what I want to do is plot the solution with the optimal model. So I'll just copy and paste this. So now I'm going to plot tau opt, or t opt. Okay. So this is going to be fit. I'm going to change this to a fit model, okay? Well, figure 4 is taken. Okay, calls figure 5. Oh yeah, and see, this is your fit model, and it goes right through the data, okay? So yeah, I think this is a great example of how to identify a parameter in a differential equation from time series data. Okay. Oh, this should not be tau. You can put in what the value of tau opt is here. So I'll do some string for it. Oh, see how long it is? What I want to do is instead round this to digits equals 1. We'll do 1 digit. Okay, yeah. So tau is 8.7. Okay, so here's your optimal tau, 8.7, and the model fits the data very nicely, which is really satisfying because this is a real data set. So yeah. Okay, and then for your activity, you'll do this for the SIR model. Okay, thanks.